Okay, well, thanks everyone for joining us. So our topic is multiple input, multiple output testing. Go to our agenda. So here's our agenda. It consists of the following. So we've got introduction, the what's and the whys of MIMO testing. Control mode is either open loop versus closed loop MIMO testing. We'll talk about how to distinguish between the two and what the differences are. Open loop MIMO specifically for modal testing in the frequency domain. We'll talk about closed loop MIMO control for applications in random and acoustic control, and those are based on the frequency domain. And then there's another one, MIMO type test, that's more for time domain testing, and that's called time waveform replication, or TWR for short. So what is MIMO testing? Just to kind of kick things off here, get us on the same page of what we mean by MIMO testing. This is, you see the structure over here. So we've got multiple independent exciters feeding energy into this system. And these are going to be it's either a structure or it could be an acoustic system. From the shaker inputs, these are starting out as uncorrelated excitation sources. And that's a very important concept there, that they are uncorrelated. And we'll go through why that is. The responses on the other end, each individual measure response will contain or can contain some amount of energy from each independent exciter due to what we call coupling. And through the complex, and when we say complex, that means amplitude and phase, these interactions through this structure or system, the energy from the sources can actually become correlated to this coupling. So that's another concept that we have to deal with in MIMO testing. The goal of a MIMO test depends on the application, whether it's modal, where we're going to be mainly in the open loop mode, measuring the transfer function and trying to achieve some really good quality transfer functions, because we're going to use that information for the modal curve fitting, or else in the environmental type of applications where we want to excite this structure and achieve some responses at some prescribed levels. So each one of these different responses will have either the same or could be even some different spectral response levels. Again, these can be either in the frequency domain or the time domain. Okay, so those are some basic concepts of MIMO testing. Now we get into the whys of the MIMO testing, and you can see some examples of very large structures over here. For modal especially, you need to have multiple inputs, and the main reason, or one of the main reasons for that, is that in modal testing, it's the only means for distinguishing between closely spaced modes. So you have to have independent, uncorrelated sources going into the system. And that's the only way that you've got really closely spaced modes in frequency. That's the only way you can actually distinguish those. And you use a multi-degree of freedom parameter estimation in modal analysis. Also, another big reason is to distribute the energy more evenly around the large structure. For example, this long, slender rocket from the Ares launch vehicle, or for aircraft, typically there's a bunch of shakers, and in this case, it's kind of an extreme case where they're using 16 shakers are mounted for this A400 Airbus aircraft. For environmental testing, the whys for MIMO testing. So all axes can be excited simultaneously, and potential reduction in test time by 2/3. So you see this shaker system, this 3 DOF shaker system, where you can excite all 3 translational directions, orthogonal directions simultaneously. So typically people will do these tests sequentially in each of the X, Y, and Z directions, but with this kind of a shaker setup, you can actually condense 3 of those tests into one single test with this 3 DOF type shaker. And bottom line is, and I highlight this because it's more representative of reality and what the structure will actually see in operational conditions. Also, some benefits: potential cost savings by maintaining smaller shaker systems instead of a large shaker system. So you can have vibration control, closed loop control, MIMO testing using smaller shakers instead of some of these big shakers. Also, possibility to exploit dynamic environmental testing for multi-purposes like modal. So if you're doing closed loop vibration control, you can possibly measure the forces into the system and use that for modal analysis too, so a dual purpose. Or you can actually use this for, if you're not measuring forces, actually use it for operational modal too. Also, fundamental concept of all of this is that success of any MIMO testing depends on boundary conditions that allow achieving the goals of the test. So how you mount the structure is very important. Also, some of the criteria by NASA and other governing bodies lead people in the direction of multi-axis testing. In fact, there's a NASA standard, this NASA Handbook 7005 regarding spacecraft testing, dynamic environmental criteria. What they say in there about multi-axis excitation. Here, they're admitting what the real environments are by saying most spacecraft components and spacecraft and structures are experiencing in operational conditions simultaneous excitation of all three orthogonal axes. That's not only true for translation, but also rotational degrees of freedom. So that's a natural environment, but current methods don't accommodate the real situation typically. And these tests would be done sequentially in three translational directions. However, they are recommending if you do have the capability or can accommodate the multi-directional testing, MIMO testing, then you should try to do that. And again, representing reality through testing. The very famous MIL Standard 810 government document also advises to be as close to reality as possible. In fact, they even make the statement tailoring is required. And tailoring implies that you want to go out and measure in the real environment and characterize either through frequency analysis or time data analysis. You want to bring that information and tailor your test to accommodate those kind of responses in the real environment in your laboratory to, again, replicate the real operational conditions. There's still work to be done, still many issues regarding standardization of multi-exciter testing, but it is becoming more common, and there are shaker systems being developed and software is being developed to accommodate this multi-axis scenario. Next, we talk about distinguish between what we mean by closed loop and open loop testing. And again, open loop is more in the context of modal testing, where you've got a shaker system and the structure, and you've got the DAC sending out signals to the amplifier and shaker, exciting the structure, and then measuring some responses. So this is not controlling the amplitude, but just measuring the responses and deriving the transfer function where we have acceleration over force, or G's per newtons in engineering units. That information is used typically for modal analysis. And then we'll eventually expand this into MIMO testing and using multiple drive signals and multiple shakers and multiple measurements and measuring kind of a matrix of transfer functions that we use for modal curve fitting. So that's open loop. For closed loop, again, just like in the single axis control system, you want to send out multiple drive signals controlling multiple controls channels to some prescribed levels. And so the DAC will send out these drives to the shaker and amplifier, excite the structure, have multiple control channels, but you can also have multiple measurement channels, and hence you derive the transfer functions from that. But typically what we do different than in modal testing, in vibration control testing, the transfer function that we measure is acceleration over drive. So it's actually G's over volts. This is depicting single axis control, but the same idea is where you want to develop this SysID transfer function by measuring the responses over the drive outputs. Open loop, MIMO testing, modal testing, and again, this is that A400 Airbus large structure with many shakers surrounding the structure, kind of an extreme case of modal ground vibration testing, GVT. And there's different types of excitation techniques. So swept sign, step sign, these are classified as what we call phase separation. And in that case, they're using 8 shakers and 8 sweeps, multiple fuel stores. So the idea here is that you've got a lot of different sweeps, very time consuming. It increases quite a lot the complexity of a test like this by adding more exciters. But on the other hand, you get better distribution of energy and better signal to noise ratio from your responses. You can also achieve perhaps maybe some operational levels of responses if needed, and that's done for linearity checks. Then also using 16 shakers, so again, spreading the energy because these are low-level signals, and you again want to distribute the energy around the structure to get better signal to noise ratio and better to excite the structure at multiple locations with a lot of shakers. in many different types of scenarios where you want to measure good quality transfer functions. And this is applicable, again, not only for in the context of mold testing, measuring transfer functions, but as mentioned, we want to measure good quality transfer functions in the closed loop multi-axis control scenario too. And on the left here is what we call these phase separation methods. So you kind of have a toolbox of different types of source signals and excitation types to excite the structure and measure the transfer function. So whatever might be most appropriate for the scenario that you're dealing with, you have different types of ways to excite the structure. So like impact, that's pretty popular. Probably one of the most popular for mobile testing is burst random. It's a periodic type random signal. Another one to choose from is pseudo-random, and I'm going to highlight this one in particular because there are some nice benefits with this method for generating a nice, good quality transfer function. And then we have swept sign and step sign, which are used mainly in the aircraft industry, but there are other applications for that too. And then exclusive, I think, to the aircraft industry would be this normal modes testing that we call the phase resonance methods, where we're actually managing the phase relationship of each of these shakers, the amplitude and phase of each of the shakers relative to each other in order to induce and excite and kind of isolate a single mode. Basically adjust the amplitudes and phases of each of those multiple shakers going into the structure to isolate a single particular mode of interest. That's important for like flutter testing and flutter analysis. For this phase separation method, we have this method called PCA, principal component analysis. So what's important and kind of implied with this name here is that we have phase separation methods. We want to have uncorrelated signals using all of these types of sources. And to ensure that we do, in order for the system to calculate a proper FRF, frequency response function, we need to have independent, uncorrelated sources. And the PCA is the tool that we have to ensure that we have uncorrelated sources from multiple inputs. So as I mentioned, this pseudo-random, I kind of wanted to highlight this a little bit more. This is a what we call multi-sign. Very simple example of multi-sign is where you have multiple sinusoids lined up on the Fourier grid. So if you have a 2 Hertz resolution, you have every 2 Hertz, every 4 Hertz resolution, you have a sinusoid of every 4 Hertz. So like in this example for a 2 Hertz resolution on the Fourier grid, we have a 2 Hertz sine wave, a 4 Hertz sine wave, and a 6 Hertz sine wave. And looking at those in the time domain, this is what we have up here. Now, if we add those up, which gives us this purple trace, we can see there's some constructive and destructive interference between these sine waves, which can be good. But if we manage the phasing of these different sinusoids, then we can kind of control these amplitudes and how they interact with each other. And that's one of the ideas here that we have with pseudo-random and kind of an option with our pseudo-random that we have available in Test Lab. So there's a couple different forms of multi-signs. We call it periodic random. The amplitudes are randomized and then the phases are randomized, and we put that together. But again, each of those sinusoids are distinct on the Fourier grid. We also have pseudo-random, which is a fixed amplitude but randomized phases. So we can fix the amplitude and then we can manipulate the phases so that we can control that interference of those different sine waves. And that's what we call these Schroeder signs. Looking at the typical pseudo-random in the time domain, we see that in the red trace, and in the green trace is this Schroeder sign type signal. Where the benefit is kind of depicted in this display here. Whereas concentrate our spectral energy just in the small frequency bands of interest, for example, we can do this as an option. We can tailor the frequency content and focus the energy that we're applying to the structure only in the areas of main interest, and that would be the peaks of our FRF, where we get good signal to noise ratio. But also we can manipulate the phases. So this red trace up here shown in the frequency domain, you can see we can get some spurious peaks in the excitation. And this is on a log scale, so that's quite a large deviation. But with the green trace, which is our Schroeder sign, we can control the crest factor, which is the peak to RMS ratio. We can control that much better and avoid overloads. We can actually turn up the volume and still avoid overloads. And let's see, just to show you what that sounds like, see if this works. this is what it sounds like with these Schroeder signs. So we're listening to these time traces up here. So it's kind of a sine stream. Again, it's periodic sine stream. It sounds kind of weird. But that's what we're listening to. Now, the implications of that is in the transfer function. And in this case, it's the FRF for modal testing where we have G's over newtons, but the same applies for G's over volts for closed loop vibration control. So we want a good quality transfer function. Now in modal testing, it's the peaks that are most important. And here's an example from 10 to 80 hertz on a real structure. And if we zoom in from 50 hertz to 80 hertz of these peaks right here, we can zoom in and see the differences between a burst random versus pseudo random. So we're overlaying the FRF from both cases on top of each other. The blue is from the Schroeder signs and the red is from the burst random. Now the quality of FRF is depicted in the coherence function, and that's what we're seeing over here with this green trace versus this purple trace. The purple trace is from the pseudo-random Schroeder signs, and it's almost perfect coherence, whereas we have some dips in the burst random type test. Now that's important for modal testing, but if we look over here, we also have not only at the peaks the better quality FRF, but even in the valleys of the FRF, we have better fidelity in measuring the FRF. And why that's important, it will become clearer when we go into the details of the vibration control, is that we're going to measure these transfer functions, and this would be G's per volt, but even the valleys will be better measured, and because we're going to be inverting the transfer function matrix in order to generate proper drive signals. So even for vibration control, these are very important. Even the valleys are very important. Phase separation methods, as I mentioned, we want to have uncorrelated sources. And again, this PCA or principal component analysis is a tool that we have to view on the screen during the measurements that our sources are uncorrelated. This is a case where we have two independent sources, so two shakers, and we picked out of all of our responses, we picked one response, and that's probably at one of the drive point responses. A good example of a good PCA and what we're trying to look for is that we have two principal components on about the same order of magnitude, and you see that in the red and green trace. So those are two independent sources. We do have some dips in some areas, so like that could be where we're not having two independent sources but only a single independent source, and that could be maybe due to some coupling between those two shakers, some pretty strong coupling, and we can't distinguish one source from another, which is not a good situation. And then with the blue trace, we have a dependent response. So that's how you interpret this information. We've got two independent sources and one dependent response. So all the energy from this response is due to these two independent sources. A bad scenario would be over here. So like we've got two independent sources, but we've got one unmeasured input. So all of the energy going into the system is not accounted for in that response. So that's how you can interpret that. And then over here is we only have one independent source, which is not a good situation. This is probably typical when the shaker is not turned on or the amplifier is not functioning or some problem with the setup. So these are kind of things that you use in a pre-test check during a modal test. So in the end, the goal is to achieve really good quality, high fidelity frequency response functions for modal testing. Now for vibration control testing, we want also good quality transfer functions, but a different type of transfer function. Now we go into closed loop MIMO control, and we'll talk about the random version for structural testing, and then we'll talk about acoustic control for acoustic applications, and these are going to be based in both in the frequency domain. So for single axis control, there's some real benefits that are being found out about multi-axis control testing. And we typically compare that to single axis control. And whenever any new methods are introduced and proposed, you want to compare that to de facto standard, the traditional standard way of testing. There's some studies that have been taken to prove the differences and the benefits of multi-axis testing compared to single-axis testing. So in some cases, it can lead to over-test, and sometimes it can lead to under-test. And you always want to have these questions in your mind. What if it breaks? Did I over-test it? Or what if it doesn't break? Did I under-test it? So you always got to kind of have those questions in your mind when you're doing these types of environmental tests. Single axis vibration does not induce the complex interactions in multiple directions, which are normally seen in operational condition. If you can look at this structure over here, the way this missile is mounted in its rack, and how you're replicating that in the laboratory with a single axis controller, it looks like the boundary conditions are probably could be pretty close to reality. But if you're looking at this, you're shaking in this vertical direction, and it's shaking in the vertical direction, but it's not shaking in exactly the same direction. Most of the vibration would probably be in the vertical direction. So there's probably a lot of lateral motion too, but again, that's multi-degree of responses in operational conditions, whereas you're only exciting in a single axis direction in a laboratory. Over here, you can see single axis controller. Now the boundary conditions are quite different than what you would see in reality. So that's probably not a good replication of what reality is. In fact, so in most cases, attaching a structure to a high impedance shaker significantly alters the dynamics of the structure as shown over here. Better energy distribution for large or slender structures, another benefit to MIMO testing. But also always keep in mind the boundary conditions. So you want to match the boundary conditions as close as possible to replicate the real responses. So anyway, in the end, you could say the goal would be to expose any problems in the qualification stage with realistic replication of the expected dynamic environment, which I think can arguably be done better with multi-axis testing. Closed loop control, again, this is typical for even single axis control. In fact, that's depicted over here, but we're going to expand on these concepts into the multi-axis domain. So we'll have, again, multiple drive signals, we'll have multiple control signals, but again, the concepts are the same, whereas we're measuring the responses and deriving our transfer functions or SysID, which is G's per volts, but we're going to have a whole bunch of these depending on how many control channels we have. And there's some crosstalk between these different drive voltages, as mentioned in the first slide, the coupling between these different responses through the structure. And so we have to measure the spectral matrix of the transfer function or the SysID matrix. Here's our SysID. We're measuring the response over the drive. We've got G's per volt. And so we're measuring the voltage out through the amplifier, through the entire system. That voltage is going through the system, exciting the structure, and then we're measuring the G's coming back. Now we want to convert that into a multi-degree of freedom case where we have multiple amplifiers, multiple excitations. This is a 3-DOF shaker setup. So in this case, we've got X, Y, and Z shakers, and we have X, Y, and Z drive outputs. And then we have multiple control channels up on the shaker. And typically for this scenario, you would have one control for each direction. So it would be a 3x3 transfer function matrix. So we convert those into matrix form, and that's depicted here. So again, we have shakers here, responses over here, shaker excites, get some response from response point 1, and that's that component of the SysID or the transfer function matrix. You excite at this shaker, shaker M, and you get response at point number 1. And so again, that's an off diagonal term that represents that component of this transfer function matrix. So we have, in this case, an L by M. So we've got M number of shakers and L number of responses. That's an L by M matrix. So we have our drives, we have our SysID transfer function, and then we have our responses. In order to derive the drives, we have to do a matrix inversion. So again, that's where those valleys come in. So this is where we have to invert that matrix in order to calculate the drives to update the control, because we want to achieve a particular response over here at these response points. But we have to know what drive to output from each of these shakers. So we have to invert that transfer function matrix and multiply that by the target responses, and that gives us our drives. So the SysID, and we're going to verify this. So we're going to measure the transfer functions and measure our SysID, and then invert that down here and do a system verification. System verification is kind of like think of it as a self-check. What we call for single axis testing is a self-check. So we excite the structure with some low-level uncorrelated random, or it could be, again, pseudo-random signals. And the idea is to measure the transfer function here. And then we're going to invert that transfer function SysID matrix and use that to calculate our predicted drives at full level. So we're going to do that verification where we extrapolate up, know our full level responses using our low level transfer functions, and we're going to predict what we're going to see at full level. So that's our so-called self-check for multi-axis control. We call it system verification. I don't know why we changed the name, but that's the way it is. Okay, so here's kind of a series of calculations that goes on for MIMO closed loop control, the calculations that are done. So this can be either a square matrix, the transfer function, the SysID, like we had a 3 DOF shaker, we had 3 shakers and 3 control channels. That's a 3x3 square matrix. Or the idea is to have more number of responses or control points than you have exciters. So in order for things to work right, we have to have more responses than we do exciters, and that gives us a rectangular configuration in the system matrix. Here's an example of a square matrix where we have a 5x5. The transfer function matrix between the control points and the drives is measured. That's the M by N. System's transfer function is pseudo-inverted, meaning that we have, for rectangular control, we have to do a pseudo inversion. And then target spectral density matrix this is kind of like our target spectrum. So this is the target spectral density matrix is what we call this. That's what we're trying to, this is our criteria for a successful test. We have to achieve the spectrums that are represented by the spectral density matrix. So that's our target spectral density matrix. Then we have drive spectral density matrix, and that's an N by N square and just terms along the diagonal. And then we take the error between our target and control responses, and the idea is that we want to reduce the error in the algorithm. We'll try to reduce the error between the targets and the measured responses of the spectral density matrix. So that's the concept of control for multi-axis control. So this target spectral density matrix, where it comes from, it can be measured in the field. So like you have operational conditions where you have at the nose, you measure the PSD at the nose, you have PSD at the front, you have PSD at the mid, rear, and tail. There's 5 response points on your structure, and that's measured in real operating conditions. And that gives you the diagonal auto spectral density, or called PSDs. And this is how it's depicted in a graph, and you'll notice it looks exactly like it does for single axis control. Exactly the same format, exactly the same units and all. So that's our PSD that we use to control on the diagonal. On the off diagonal, we have CSD, or cross spectral density, and that's also PSD format as far as the amplitudes go. We also have phase relationship. And the phase gives us a relationship between these different response points or control points. So the CSD between the nose and the front, CSD between the nose and this point, and nose and this point, and nose on that point. So that's the cross-spectral spectrum that we measure in operational conditions, and that gives us our target of what we want to achieve in the laboratory. Now these ASDs, or we'll call them PSDs, or cross-spectral densities, there's some relationships between these, and those are depicted here in this coherence. So there's a relationship. This is the cross-spectrum and the auto spectrums of these different points, and that gives us we can quantify the amount of coherence between those different points. I don't have the coherence shown here, but you can derive the coherence based on these different functions here. Just like in single axis control, we have abort criteria, and that's depicted here for the PSD. So our reference is going to be the green one. That's the level that we want to achieve, frequency by frequency line basis. but we also have these abort and alarm criteria too. And same goes for the CST. So again, this is a matrix of control. We're going to control each one of the control points, but we're also going to, in the algorithm, it's going to try to achieve this cross spectrum information too, because that's part of our real operating conditions. So that's the basic concept of control. Now we want to show this as an example and some of the benefits multi-axis control and why you would want to maybe do this. And this is demonstrated with an example study. So the spectral density matrix is meant to represent measured field data that describes the vibration present on a structure due to its service environment. Okay, so that's our target spectral density matrix. In single axis control, you would only have just this one component, but in multi-axis control, we're going to expand to multiple points and multiple cross spectrums between those different control points. So that's depicted in this, what we call spectral density matrix, and that's our target. And the idea with this is to show that if the field boundary conditions are suitably simulated in a lab, the study that was done also shows that response to other non-controlled parts of the structure will also respond in a manner that is quite similar to what is observed in the field. In other words, the natural response of the entire structure can be achieved at all points, even if they're not controlled. So the more control points, the better you're going to be able to achieve real life operational conditions. And that's the goal of this study. And we actually have a setup here in our lab and we can demonstrate these concepts with this long slender missile where we have two shakers, shaker 1 and shaker 2, and then we have 1, 2, 3, 4, 5 control points, or sometimes they're responses and they just go for the ride, or sometimes in this study we use them as control points. So to demonstrate this, first of all, our step 1 is to basically just excite the structure, just to kind of, with these, this is suspended by bungees. You can see those here. There's some hooks right here. So we were in a kind of a free condition. Now we want to show this, we want to excite the structure with just some continuous random excitation, and then we're going to just simply measure the responses that we get from this. So that's step 1. And that's to kind of simulate operational conditions. So we're going to generate our operational real life conditions with that. And then we're going to use acceleration from these responses, and we're going to build our target spectral density matrix, which consists of these PSDs and CSDs, which is shown down here. So we've got missile 1, 2, 3, 4, and 5 versus missile 1, 2, 3, 4, and 5. That's going to be our 5x5 spectral density target matrix. Now, to show the concepts here and the benefits of multi-axis control, we'll first of all do a single axis control. And this is kind of in a way going to show some weakness in the single axis control scenario. So we use that PSD from channel 1, and we're going to use shaker 1 to control and do a closed loop control just between shaker 1 and control point 1. And then we're going to basically just observe the responses and show how they compare to the real life conditions. Then the second part is do MIMO control, and we use two control channels, point number 1 and point number 5, and we're going to do closed loop MIMO control with shaker 1 and shaker 2, and we're going to do a closed loop control between 1 and 5. That's going to be a 2x2 target spectral density matrix that we're going to use between point 1 and point 5. And then finally, we're going to use all 5 of these points, and we're going to generate, do closed loop control using 5 control PSDs, and we'll use the full 5x5 target spectral density matrix. So that'll give us our 5 PSDs and 10 CSDs. And then step 4, we'll just show the results. So that's the test that we do. So first, the structure is excited with continuous random signal at both shakers. Measure the 5 control points. There's our PSDs, there's our CSDs. So those are our field conditions that we're going to simulate. Then we're going to take that information, and to prove the point, we're going to do closed loop control. And the objective, control point 1, single axis control, show closed loop control is excellent. And then look at the other points, and even though control is good at control point 1, the response at all other points shows over testing and under testing. And then we'll use this 2x2 control at point 1, point 5, show closed loop control is excellent at those 2 points. However, even the control is good at those 2 points, the responses at the other 3 points are still under testing or over testing, but still better than this first case. And then finally, using the full 5x5 spectral density matrix, we're going to control at all 5 points, and we're going to show that all points match PSD objective and also that all CSDs also match the objective. And we're achieving real life conditions. So here's the results. PSD, our single control channel, excellent control between point 1, shaker 1 and point 1, but severe over testing and under testing at all of the other points. And these are log scales, so even though it might not look like a lot, there's some very severe over testing and under testing going on here. Then we go to the second case where we have 2-point control. So point number 1, point number 5, those are controlled very nicely. Those would be very nice, acceptable results. However, if we should want to look at the other points and compare those to what we should be achieving, you can still see some degree of over testing and under testing. Now, if we go to the third case where we're controlling at all 5 points, now we've got very good control at all points, but what is also important is the CSDs, the cross spectrums between all those different points. So this is comparing with single exciter, single axis simulated operational data. In the first case where we've got good control between shaker 1 and point 1, but if we look at the CSDs between all those other points, we can see some severe over testing and under testing at those other points. If we go to the 5-point control, simulated operational data, not only our PSDs, but our CSDs are also very well matched. And if you would look at other points on the structure, even if they're not controlled, any other point around that structure will show similar results to what you see here. So that's the whole concept, the whole idea of this study. And this was an excellent paper for reference. This was written by Phil DeBourne of AWE in the UK. And he used the concepts that were just presented for that example is exactly what he did here too, although he had a different setup. But he's depicting what's typically done in real testing, in the real test world, where you've got a single shaker and you're trying to achieve some vibration responses around the structure and how that compares to multi-axis testing. This is a simulated missile, and he's got a bunch of piezoelectric shakers around this structure. And so he showed the single axis case and the multi-axis case. And through this paper, he was coming up with the same conclusions that we just came up and were presented in that example. So next, we'll go through the agenda. We'll show random acoustic control, frequency domain. So we'll show acoustic control. We just showed the random structural control, so we'll show acoustic control. And in MIMO acoustic control, we're going to try to, in the laboratory, induce some acoustic response around this structure in order to depict the real operational condition. These spacecraft will see some extremely severe acoustic environments as they're launched up into space. So basically, before they get up into the heavens, they got to go through a hell of a lot of acoustic noise as they're being launched into space. This is shown in a typical reverberation chamber. So we call this reverberant field acoustic testing, or RFAT. So this is a very expensive chamber, and this is just a single component, but a lot of times a full spacecraft would be tested in a chamber like this. And you have these woofers, subwoofers, mid-range, tweeters, a bunch of different speakers in this solid cement reverberation chamber. So you're trying to get up into the same acoustic levels that the spacecraft and components would see as they're being lifted into space. Instead of using a very expensive reverberation chamber, or some customers don't have these reverberation chambers, so they are at the mercy of companies that do, and sometimes even they are competitors to each other. And so with what we call DFAT, or direct field acoustic testing, it can be an alternative to RFAT, reverberation field acoustic testing. So compared with RFAT, these can be less expensive. These are just a bunch of speakers, and literally they can use these same speakers for concerts and playing music. The setup here can be a lot less expensive than a reverberation chamber. They're more convenient for companies who don't have an RFAT facility. So you can take this and set it up anywhere you want, even outside if you wanted to. But of course, you're going to be exposing these to some extremely loud levels. Again, you want to achieve that acoustic volume similar to what it would be exposed to in space during the launch. And these levels can be in excess of 145 decibels. So if you went and stood in here during a full level test, that would probably shake you to death and probably kill you. Those are extremely loud levels, but these components are exposed to those levels as they're launched into space. Now for this application, for the acoustic application, the same control software and control concepts that we're talking about prior to this are the same as for the structural case. So all of the same software. Now the units and the success criteria are different because you're dealing with acoustics instead of structural vibrations. So instead of accelerometers, we use microphones, and instead of shakers, we use speakers. And this was set up done at our engineering services facility using a setup, and this is an acoustic chamber, an hemianechoic chamber where we did this testing. A typical setup, this is depicting the speakers. This is a single, what we call stack of speakers, and the stack of speakers is shown over here. So low, mid, high speakers, and there's 8 of those. And then we have subwoofers over here. And these are subwoofer speakers, and these different speaker components can excite different frequency ranges, and that's depicted in this diagram down here. So this is showing the spectral response of the subwoofers. They can achieve the low-level responses, and then the LMH, the low, mid, high speakers, can achieve the higher frequency ranges. You couple those together, and this is what you see in the spectral response, and a number of these different speaker stacks. Each one of these stacks is a independent drive. So one drive goes to this crossover filtering, and that splits it up into these different speaker components. So the sub would be in this area, and the crossover filtering takes care of that. So the drive signal for each stack is sent out. You could think of these as a single shaker. So in this case, there would be 6 shakers and a bunch of control mics. So in this case, we have 6 independent sources and 12 control mics. So that gives us a 6x12 matrix that we have to calculate the transfer function, invert that transfer function, and update the drives as we do that closed loop multi-axis control testing. So that's DFAT, speaker arrangement. And these are some of the results. This is like 143 dB reference spectrum here. And you can see that the spectral energy drops off quite a lot as you go up higher and higher in frequency. In fact, these are both log scales. So in the y-axis is in dB and octave format down here on the x-axis. So these are both log scales. If you analyze this, you can see this is for one particular control channel, and this is the PSD in acoustic units, pascals, and that's my PSD at one component of the spectral density matrix. And this is going to be the same spectrum for each of these control points. We also have off-diagonal terms, so there's, for each of these control mics, there's going to be some CSDs in the off axis. So this is our, again, the so-called spectral density matrix that is our target matrix for this application. This is the results shown for all of the control channels, which are averaged. So you can see very good uniformity and very good results here, very good control. One other aspect of this I wanted to point out is that you can see kind of an interesting aspect here is that 75% of this acoustic energy is focused in only 3% of the entire spectrum. So again, these are log scales. So this is 3% of my entire spectrum, but I've got 70% of the acoustic energy focused in that small narrow band, 3% of the entire spectrum. The last case here is the time domain. The idea here is that this is typically for automotive applications where you want to drive around this test track maybe 1, 2, or 3 times and take that information from some information on your vehicle, some response information, and reduce that to something you can apply in a laboratory. So you want to take those time histories and replicate those in a laboratory. So we're going to do this in the time domain. With this technique, there's kind of a mix of using spectrums and time, but in the end, our goal is to achieve a time waveform replication of different points around the vehicle. And again, for replicating this, our boundary conditions have to be very close to what we would see out in the field, and that's crucial for success. In this case, for time waveform replication, uses the exact same time history. You can use the exact same time history or do some averaging, for example, in the time domain to depict what you would see in operational conditions. And this can be applied in single axis or multiple axis. So these are typically hydraulic shakers because we're going to be dealing with the low frequency range but high amplitudes for durability applications. So we want to use the exact same time histories, higher amplitude, lower frequencies, system level testing on a full vehicle as shown over here, or for like an earthquake application, you might want to put some electronic boxes onto the shaker. This would be for the single axis form, but for multi-axis, this is a typical scenario for multi-axis, and we call this a 4-poster hydraulic shaker system. And note boundary conditions here, if we control at these tire locations or the axle locations, and if we measure those in operational conditions, our boundary conditions are pretty close to what we would see in operational conditions. So this is a very achievable type of test where we want to replicate those time histories at each one of these excitation points. And we can also use that to replicate responses at any other point around the structure, basically because we have really good representation of our boundary conditions in the laboratory. So again, with this form, the time domain form, we're going to use some spectral information and we're going to calculate these just like in the structural case. We're going to measure our SysIDs because we want to derive our drive voltages in the time domain, send those to the shakers, and then we're going to measure our responses, but in this case, we're going to use time domain responses, which we want to control to. This is target trace, for example. This is what we want to achieve, and if we zoom in on that narrow point in time, we can see this is our time domain response at a particular point on the structure. We can also look at the frequency response and see how that compares to if we took a chunk of data out of here or took an average of this time data and calculated a bunch of spectrums and averaged those together. We can also use that as kind of success criteria too. The way we control this, and there's different choices of control and how the control is done. So this is what we call online adaptive control, and this is actually done in the frequency domain. We can actually do this in real time, updating our transfer function or SysID in real time and kind of adapting on the fly as we're playing out the signal. We can achieve a better transfer function. And we do that in the frequency domain, but in the end, we want to, again, achieve a better time domain target. Also, another choice is to do offline adaptive control where we play out the entire time trace and again, update the transfer function and calculate the inverse transfer function by inverting that transfer function. Once we get some good established transfer functions, then we can maybe switch over into the time domain. So there's different strategies of how you conduct a time waveform test, where maybe as a first phase, get a good quality transfer function through these different types of controls strategies, and then eventually make some corrections to your responses in the time domain. And it actually looks at time data, the target and responses, and make some adjustments to the drive to achieve the time waveform replication. And then eventually for automotive applications, you want to take that time data and just basically loop through and with no control. Once you have a good drive waveform that you're going to excite the structure with for each of the inputs, then you can just sit back and let the system run, and you can do that for a number of different cycles. So one complete time trace could be one cycle around that test track, and then you want to do that maybe 100 or several hundred times or whatever it is. So to look at the results, here's some different ways to depict the success. And basically looking at the time trace of your target overlaid with the measured responses, and then subtracting one from the other in the time domain and looking at the error between the two. So that's what's shown in this display here. Also in the time domain, you can plot one against the other So in a perfect case, if you had all of this time data lined up on top of each other and you plotted one on one axis in this XY plot versus the other axis, the idea is that you want to see a perfect diagonal, a very straight, sharp, narrow line along this diagonal, and that's really good results. These are kind of marginal results here. And you can see this information as you're acquiring data. Also, as a post-test evaluation, you can then overlay, after you've done a few iterations to achieve drive signal, you can see how results line up. And again, zooming into the data and then looking at the error. And then also, again, you can do some spectral processing and spectral averaging to look at the spectral response of the target versus the measured. So thanks for attending. If you have any questions, you can send me an email if you feel like.